Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that is easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos, and comment below on videos you would like to see in the future. Today I will be going over E, also known as Euler's number. I will address 4 ways to define the constant and 4 of the many ways it's used in mathematics. E is a number that is approximately equal to 2.71828. It is often called Euler's number, named after Leonhard Euler, who did extensive work on the constant. But how is it defined? The first definition I'll address is defining it using the factorial function. The factorial function is denoted using an exclamation mark, and the way it works is that you multiply your number by all the previous counting numbers. Here we see that 3 factorial is equal to 3 times 2 times 1, which is 6. Showing another example, we see that 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is 120. It is also important to note that 0 factorial and 1 factorial are just 1. In our definition of E, we're going to look at what happens when we evaluate 1 over n factorial for all positive counting numbers and 0, and then continuously add them together. The reciprocal of 0 factorial plus the reciprocal of 1 factorial plus the reciprocal of 2 factorial, and so on, actually gets closer to E the more terms we add. This may seem confusing, so allow me to explain. First, I'll start to evaluate the factorials in the denominators. This leaves me with this. Now I'll start to add them together. We can see that as I continue to add the terms together, I get closer to E, and the more terms I add, the closer I would get, infinitely. This relation can be mathematically written out like this. This kind of representation is called summation, and I will explain what it means. Here, the n equals 0 is saying that we start with 0 in our sequence, which we can see us doing here. The infinity represents how we're going to continuously add more terms to this sequence infinitely, which we can see us doing here, as the denominator gets larger. And of course, the 1 over n factorial is showing what our sequence is going to look like, continuously adding 1 over n factorial as n gets larger. Now I'll move to my second way of defining E. The second way to define E is to visualize how it can be used in area measure on graphs. Here we have the graph y equals 1 over x. It turns out that the area under the red curve between 1 and E is exactly equal to 1. Though it's a very specific and wordy definition, a common definition of E is the number for which the area under the curve of 1 over x from 1 to that number is equal to 1. Later in this video, I'll provide a more detailed analysis of this, but for now, I'll move on to my next definition of E. Another way to define E is expressing it as a limit approaching infinity. Allow me to show what this means. This is a common way to define E, using a limit notation. If you're unfamiliar with this, what we are doing is we are analyzing what 1 plus 1 over n to the n power looks like as n gets closer to infinity. So, starting with n equals 1, we can evaluate this. We find that it equals 2. So, now let's see what happens as n gets closer to infinity. We can see that as n gets bigger, our number gets closer to E, although it's still far off right now, so let's try going bigger. Let's see what it looks like when n is equal to 1,000. There we go. Now we can see our number starting to look like E. As n gets even larger, we can create an even greater approximation of E. Now I'll move on to the last definition of E I'll go over in this video. E is often defined by its unique characteristics when it comes to the rates of change. Let's look at the expression e to the x power. This is what our graph e to the x looks like. Another way to think of the rate of change of a function at a certain point is to look at the slope of the tangent line at that point. This expression, e to the x, has the unique property that the rate of change is equal to itself, or, in other words, that the slope of the tangent line at a given point on that graph is equal to the y-coordinate of the point. Let's see what this looks like. We can see the red line being the tangent line at the point where the function is equal to 1, and we can also see that the slope of the red line is also equal to 1. Again, we can see that the tangent line at the point where the function equals 2 has a slope of 2, and this continues for all points on the graph. This relation is crucial in the study of calculus, since e is a unique number that exhibits this property when raised to a power. Now that I've gone over 4 common ways to define e, I will now go over some of the many ways it is used in mathematics. One of the more common uses of e is acting as the base of the natural logarithm, also known as the natural log, which is a crucial function in mathematics. The natural logarithm, denoted as ln of x, is defined as a number for a given x, for which e to the natural log of x is equal to x. So, let's see what this looks like for particular values of x. Due to our definition, we know that e to the natural log of 1 is equal to 1. This leads us to know that the natural log of 1 is equal to 0, since e to the 0 is equal to 1. Evaluating the natural log of e using our definition shows us that e to the natural log of e is equal to e. This shows us that the natural log of e is equal to 1, since e to the 1 is equal to e. This is what the graph of the natural logarithm function looks like. It plays many roles in mathematics, and next I'll explain one of its many uses. Remember earlier in the video where I said I'd give a further evaluation on this definition of e? I'll now do this using some calculus, but since many of you are probably unfamiliar with calculus, I'll explain to you what I'm doing as if you don't know it. Recall that what we're doing here is we are seeing that the area under the curve of 1 over x from 1 to e is equal to 1. So let's see what this looks like using math symbols. This is an integral symbol, and it is used to represent the area under a curve. These numbers are our limits of integration, and since r's are 1 and e, we see that we are finding the area under the curve from 1 to e. The function in the integral tells us what curve we are finding the area under, and here we are finding the area under the curve of 1 over x. The dx here is telling us which variable we are working with. It is dx because we are working with the x variable. If we were working with the y variable, for example, it would be dy. As it turns out, the integral from a to b of 1 over x dx is equal to the natural log of b minus the natural log of a. If you would like to see me prove this using a calculus, let me know in the comments. I won't worry about proving it in this video, though, in order to not distract from the point, which is showing e's extensive uses in mathematics. So, using the equation in the top right, let's evaluate this problem. We can expand this to equal the natural log of e minus the natural log of 1. And recall from earlier in this video, we showed how the natural log of e is 1 and how the natural log of 1 is 0. So we can write this as 1 minus 0, which is just 1. And of course, this is the answer that we should have, because that's what we were trying to show, how the area under the curve from 1 to e is equal to 1. So, now that we've gone over a first use for e in mathematics, along with a popular example of how it is demonstrated, I will now move on to another use. E is used very often in the study of imaginary numbers, which is an interesting topic in mathematics. Despite their name, imaginary numbers are far from imaginary, and are instead a very advanced and fascinating topic in mathematics. The constant I, as many of you may be familiar with, is defined as the square root of -1. Additionally, many of you are likely to be familiar with pi, defined as the circumference of a circle divided by its diameter. Well, a really interesting property involving these constants is that e to the pi times I power is equal to -1. If you would like me to show why this is true, leave a comment. For now, I'll just leave it as it is, as one of the most unique identities in mathematics. This is called Euler's identity, and has many uses in the study of imaginary numbers. Now I will go over yet another use for e in mathematics. Defining trigonometric functions. If any of y'all have studied geometry, you may be familiar with right triangles and trigonometric functions. Here we have a right triangle with sides A, B, and C, and an angle theta, which is a symbol that looks like a 0 with a line through it. You may recall from studying geometry that the sine of the angle is equal to the opposite side of the hypotenuse, which is A over C, and so on for the other functions, cosine and tangent. I won't go into detail on this because it would again distract from the point of the video. But if you would like me to make a video on this topic, leave a comment. The point of discussing this right now is, interestingly enough, these functions can be expressed in terms of e and imaginary numbers. Here we can see these functions being defined. It may come as a surprise to some that these functions, which oftentimes just deal with an angle within a triangle, can be expressed using e. But alas, e plays such an important role in so many areas of mathematics. Another equation that comes from this is Euler's formula, which is that e to the theta I power is equal to the cosine of theta plus the sine of theta times I. This formula is used extensively in mathematics to evaluate problems involving exponents and imaginary numbers. There are so many uses for e in mathematics, and I've already gone over some of them, but I'll go over one more before I end this video. E also plays an interesting role in analyzing many graphs. I'll go over one example of this. This is a graph of x to the x power. Notice this point down here, which is the lowest point on the red curve. As it turns out, this point is at the x-coordinate 1 over e. This is a great example of how e shows up even when we aren't looking for it, since one may not expect to see e in the seemingly simple expression x to the x power. If you would like me to show why this is true, leave a comment. So, I've now gone over 4 ways to define e and 4 ways it is used in mathematics. I hope you learned how e plays such a crucial role in the study of mathematics. Most of the topics in this video I just briefly referenced, so if you would like a further evaluation on any of them, let me know in the comments. I would recommend playing around with the number e and looking into its many uses in mathematics. Farewell for now!